Okay, hi. Now this is my video number 2029. Okay, so in this video I'll talk on the convolution theorem. Alright, the convolution theorem. Look at your notes. Convolution theorem. So I think it's clear. I hope that. So the definition of the convolution itself is that if the convolution of two functions, which is integrable f and x, so we use the operation star there. Yeah? So f star x is given as this. So if I can write down those things, the convolution of two functions fx and gx, both are integrable, which we denote as f of x star g of x. This is we define as 1 over square root minus infinity to infinity f x minus zeta g of zeta d zeta. Yeah, so that's a definition of convolution. Now, if we find the Fourier transform of the convolution of f and g, yeah, the Fourier transform, just I think I better just read from here, but it seems quite small, right? I hope you can see those things. Okay, so the convolution of the Fourier transform of the convolution of f and g is given by that, where f is the convolution of the Fourier transform of f and gs is the Fourier transform of g, and for the inverse Fourier transform is given by, which is we obtain fx and gx, which is the inverse of the Fourier transform of f and g. Or you can write this, yeah, this is from the definition of convolution here on the left side, and on the right side, this is the inverse of Fourier transform of f and g. Okay, so it's not difficult to see for these parts here. You just use the definition of inverse Fourier transform, then you can see easily those things. And as well as for the Fourier transform for function f and g. So let's prove for the Fourier transform for f and g. So we have the Fourier transform of f, convolution of f and x. This is by definition is given as we have, this is f of s, g of s. So we're going to prove this. Yeah, we're going to prove that. So f of x, g of x, s. This is given as 1 over that, integrate from minus infinity to infinity, we have fx star gx e minus isx dx, right? And we use the definition of convolution, then we have, this is given as 1 over that, integrate minus infinity to infinity. The definition of convolution is given here, so we have 1 over 2 pi minus infinity to infinity. Okay, so we have f x minus zeta, g of zeta, and we have e I negative isx dx. Okay, and of course for I here, e minus I as x, I can write this as a e to minus I as x plus I as zeta minus I as zeta. Okay, then I can factor out those ei minus I as zeta. We can take it out. So this is equal to, so I don't want to multiply these two because we're going to have a Fourier transform of two functions. So I keep that 1 over sec 2 pi. So we still have 1 over sec 2 pi, then integrate minus infinity to infinity. So for this I can factor out those gx. I put it here. I miss one more here. Should be d zeta. So g zeta. Then we factor out e minus I as zeta. Okay, d zeta. And then I have another one here. 1 over square root 2 pi integrate minus infinity to infinity. That f x minus zeta e I, you can factor out I, you can factor out s, so you have minus I is here, so we have x minus zeta s d dx, right? So that's dx. So you can see this is the definition of the first part here, the definition of Fourier transform for G, and the second part here is quite clear, but if you can substitute that with some variable, let's say nu, that, so what you can see from there, this is just that part is just 1 over sec 2 pi integrate minus infinity to infinity f nu e minus I nu s d nu. Okay, so if this part here, that give you g of s, and this part here give you f of s, means this is the Fourier transform for G, and this is the Fourier transform for S. So you end up with this is just gs and fs. Okay, so that's a definition of the proof for the Fourier transform of two convolution function, right? So next part is we look at the possible relation. Okay, what is possible relation? I think this is too high. Let me make it a little bit lower. Okay, I think that's better. Okay, now the possible relation from the definition of inverse Fourier transform here. This is the inverse Fourier transform, because this is what you have fx gx. Yeah, if you, this is fx gx. Okay, and if you put x equal to 0 inside there, so what we have, this is f zeta still there, so x is 0 g minus zeta, and the right hand side we put it x0, then we end up with this. Okay, and then if you use this substitution and use the properties that I mentioned earlier in my previous videos, that if you take this and f inverse f of minus x, the conjugate of those, so you can write in this form. This is not difficult to see. Yes, from gs is the Fourier transform of G. You substitute this G with that, so you end up with this. Okay, the Fourier transform of conjugate of f minus x is just the same as the conjugate of the Fourier transform of f So that gives you the conjugate of Fourier transform of f. Yeah. So using this this definition, so you can see that GS is equal to f, the conjugate of fs. So you substitute into there, so you have there, this is fx, this is f conjugate of s, and the right hand side you have fs there, and GS is the conjugate of fs, and you end up with that relation. Okay, so you end up with that relation. So this is what we call as the possible relation. Yeah, we call it as a possible relation. So you can see that this result is known as possible relation. It is important in many signal processing application. So this integral minus infinity to infinity fx squared dx can be thought of as energy of a signal, and on the right side you have integral from minus infinity to infinity absolute of f s squared ds is we measured and known as the power spectrum. Okay, so for the Fourier transform of the generalized function, and that's the end for that. I haven't taught you the generalized function, yeah, so therefore I skip this part here. I will go to in the next video the example of the use of Fourier transform in solving differential equation. Alright, for this video I'll stop here. Bye.